So our next topic over here is phenols, the compounds in which OH is directly linked to aromatic ring are known as phenols. Our OH is directly linked to the benzene ring or aromatic ring are known as phenols. Again, phenols are classified as monohydric, dihydric and polyhydric phenols. So as you can see, ring with only OH only one OH is known as phenol with one OH, and CH3 is known as O-cresol. Why O? This position is known as ortho position, right? OH ka next first position is known as ortho position. So it is O, orthocresol. Now dihydric, when I say two OH are there, see. So this is called catechol. And if my first OH and second OH is at a difference of one position only, that is first OH is at this position, second OH is at the ortho position, right, or the next position, then it is catechol. Or if it is to the difference of two positions or next to next position, it is known as resorcinol. And for example for polyhydric phenol is pyrogaltol, which is OH having with a phenol having three OH atoms or at OH groups. Now coming to the resonating structures of phenol. Now these are the resonating structures of phenol, which means what? This lone pair of electrons present in the oxygen, they shift from one position to another, making this or making some isomeric structures of the same phenol. Here you can see the first and last phenol are almost same, the only difference is the position of double bonds. Now same for the phenoxide ion. What is a phenoxide ion? As we saw, what was alkoxide? It was RO minus. Phenoxide is what? Phenol O minus, right? This benzene ring connected to O minus. So this also shows resonating structures. Okay, so this phenoxide ion also, as you can see, first one has double bond on this position, then the last one has it in the opposite position. So that is all what about resonating structures of these resonate phenol and as well as phenoxide ion. Okay, you can have a look. Now coming to the preparation methods of phenols. So, can you just believe that in this small area we have already covered the whole preparation of phenols? Okay, so quickly let's learn about them. So, the first method is when we have chlorobenzene with us. Okay, chlorine connected to the benzene ring, chlorobenzene, right? Plus NaOH in presence of 623 Kelvin temperature and 300 atm pressure, we will get sodium phenoxide. Remember, we will get this compound many times while studying phenols, that is sodium phenoxide. Sodium, this benzene ring connected to ONA, right? Sodium phenoxide. Again on reaction with HCl we will get phenol. Second one, this is benzene ring on reaction with oleum. Okay, oleum is a compound which is actually fuming sulfuric acid. Okay, fuming sulfuric acid. Oleum is what? Fuming sulfuric acid. It will give us what? Benzene sulfonic acid, right? Benzene ring with SO3H group, benzene sulfonic acid, and reacting this in the first go with NaOH and second go acidification H plus will give us phenol. You can just write this step as a same one step only. Just give the numbers one NaOH, second H plus. Okay, now coming to the third one, that is formation by cumene, right? Now this cumene is what? This benzene ring attached to CH3 group. That is isopropyl benzene. Cumene is also known as isopropyl benzene. So they may also ask you, write the preparation of phenol using cumene or using isopropyl benzene. Okay. So this on oxidation, that is O2, gives benzene ring with CH3, C, that is OOH. What is this? Cumene hydroperoxide. This is known as cumene hydroperoxide, which on acidification will give us phenol, right? Next, coming to this is aniline. Benzene ring attached to NH2 is aniline, right? So this aniline on reaction with NaNO2 In presence of HCl at 0 to 5 degrees Celsius gives us N2Cl. This benzene ring attached to N2Cl, which is diazonium salt. Okay, benzene diazonium salt. This on reaction with warm water, it will give us phenol, right? Next reaction is that bromobenzene on reaction with magnesium in presence of dry ether will give us benzene ring attached to MgBr. Okay, so this on oxidation in presence of dry ether will give us benzene ring attached to OMgBr. Again on hydrolysis or reaction with water, it will give us phenol, right? So again the next reaction is what? Next reaction is this benzene ring attached to OH and COOH. Now, what is this known as? This is known as salicylic acid or orthohydroxybenzoic acid. Here you can see if this is the position I consider as 1 COOH. So the next position is what? Ortho position. And what is my hydroxy? It is OH group itself, right? So next position of COOH, which is orthohydroxy benzoic acid. Benzene ring with COOH, benzoic acid, and orthohydroxy, right? Or simply salicylic acid. Reacting this salicylic acid with NaOH in the presence of calcium oxide and heat will give me phenol again, right? So these were the just simple how many reactions? 1, 2, 3, 4, 5, and 6. 6 preparation methods of phenols, right? Now what are the physical properties of phenols? Firstly, phenols are colorless, crystalline, deliquescent solids which give pink color on exposure to air and light. They are less soluble in water due to the formation of intermolecular hydrogen bonding. The hydrophobic forces are more, so the solubility of phenol in water is less. Hydrophobic, right? Phobia, when we say we have fear of something, that is called phobia, right? Hydrophobia, away from water. So the hydrophobic forces are more in phenols, so the solubility of phenols is less in water, right? So this phenol can be written as phenoxide plus H plus, right, as we discussed. Now this phenoxide has greater stability than phenol. Why? Because of the resonating structure, their oxygen carries a positive charge, right? Here as you can see, here in the resonating structures of phenol, oxygen is having positive charge everywhere, right? Here O plus, O plus, O plus. But in phenoxide ion, oxygen is stable, right? No charge on it in the resonating structures as you can see here. So phenoxide ion is more stable than the phenol ion or resonating structure of phenol, right? Now coming to acidic strength of phenols. Acidic nature of phenols is directly proportional to 1 by plus I and plus M effect. That is, plus I is what? Plus inductive effect, and plus M is what? Plus mesomeric effect. Which means what? If electron donating groups are present, acidic nature is less. If electron withdrawing groups are present, that is minus I and minus M effect, then acidic nature is more. Coming to the chemical properties of phenols, reactions involving cleavage of O and H bond, right? O and H are separated. So here what we have again, phenol plus sodium, we get sodium phenoxide plus half mole of H2, right? And second reaction is that phenol plus NaOH gives sodium phenoxide plus H2. Further, see, this is the difference between alcohols and phenols. Alcohols do not react with NaOH. This is the example here. See, third one. ROH plus NaOH has no reaction. But phenols can react with NaOH to form sodium phenoxide and H2O. So, these reactions indicate that phenols are more acidic than alcohols, and phenols do not react with Na2CO3. Phenols do not react with sodium carbonate. So, they are less acidic than carboxylic acids. which means that carboxylic acid can react with sodium carbonate as well, right? But phenols do not. So if we want to write the order of acidic character, carboxylic acids are more acidic, and after that comes phenols, and the least acidic are alcohols. Now coming to esterification. These alcohols on reacting with RCOOH, that is carboxylic acid, will give us this ester, that is benzene ring with OCOR group plus H2O. Further, this phenol reaction with RCOCl in presence of pyridine will give us again that ester plus HCl, and further on reaction with RCO twice oxygen will give us again ester plus ROOH. For example, if we have this salicylic acid plus CH3CO twice O, it will be a reversible reaction which will give us acetyl salicylic acid or aspirin. This is a very very important reaction because it is having a named product which is aspirin, right? So this will give me acetyl salicylic acid. Why? Because here acetyl group is present to this benzene ring with COOH, right? So acetyl salicylic acid plus CH3COOH, and this acetyl salicylic acid is known as aspirin. Now having the neutral FeCl3 test for phenols, right? So, what is the test? 3 moles of C6H5OH, that is phenol itself, plus FeCl3 will give us ferric phenoxide, which is violet in color. What is that ferric phenoxide? FeOC6H5 thrice plus 3 moles of HCl. Now coming to thylene dye test, right? Now we have also learned about phenolphthalein in our lower grades, right? It is a artificial or synthetic indicator, right? So phenol plus this phthalic anhydride in the presence of concentrated H2SO4 will give us phenolphthalein, which is pink in color, right? And when dissolved in NaOH is dissolved, it forms pink in color, right? It becomes pink in color. Why? Because NaOH is base, right? So it gives test for bases and acids. It is an indicator. The above two tests are identification tests for phenols. What is that? Neutral FeCl3 test and phthalate dye test. Now coming to electrophilic substitution reaction. First is halogenation. Now this phenols on reaction with 3 moles of Br2 in presence of H2O and Br and CH3COOH will give us 2,4,6 tribromophenol. Okay, so this is what halogenation, where halogen is what? Bromine. Okay, if we use 3 moles, this is the product that we get. But if we use only 1 mole of Br2, what will we get in the presence of non-polar solvents? Right, first case was polar solvents like water. Right, second case is non-polar solvents like CCl4 or CS2. Here we will get ortho bromophenol or parabromophenol, right? Now coming to nitration. Yeah, nitration, we have phenol in presence of dilute HNO3. It will give us what? Orthonitrophenol and paranitrophenol. Now orthonitrophenol has intramolecular hydrogen bonding, right? What is hydrogen bonding? When there is a bonding between electronegative atom and hydrogen, right? So here the molecular bonding takes place inside the atom, inside the molecule, intramolecular, right? So in paranitrophenol it is intermolecular, that is outside between two molecules. So these two are separated by steam distillation. Now phenol on reaction with concentrated HNO3, this was what? Dilute. If I react with concentrated HNO3, it will give me benzoquinone. It will give me what? Benzoquinone. So to avoid this oxidation, the pH or phenol is sulfonated and then treated with concentrated HNO3. Now how is it sulfonated? Phenol on reaction with concentrated H2SO4 will give me what? 2,4 di 2 comma 4 disulfonic or benzene 2 comma 4 disulfonic acid, right? Or phenol, because OH is also there. So phenol 2 comma 4 disulfonic acid in, again in the presence of concentrated HNO3, it will give us what? 2 comma 4 comma 6 trinitrophenol, which is also known as picric acid. Its commercial name is picric acid. Now these two are just super important reactions, which are Kolbe's reaction and Reamer-Tiemann reaction. Kolbe's reactions gives us salicylic acid, while Reamer-Tiemann reaction will give us salicylaldehyde. Okay, which is this one. So coming to Kolbe's reaction, phenol on reaction with NaOH will give us what? Sodium phenoxide again, right? This firstly on reaction with CO2, after that acidification will give me salicylic acid or orthohydroxybenzoic acid. Now coming to Reamer-Tiemann reaction, phenol on reaction with CHCl3 in presence of aqueous NaOH will give me an intermediate, okay, which is benzene ring with ONA and CHCl2. Again on reaction with NaOH, it will give me benzene ring with ONA and this CH with OH groups. So here we will do acidification and removal of H2O. So what we will get? We will get salicylaldehyde, that is a benzene ring with CHO group, benzene phenol with CHO at the next position here, right? So this is salicylaldehyde. Now coming to the next thing, that is reaction with zinc dust. So this is the second last reaction for phenols, right? So reaction with zinc dust. So this phenol on reaction with zinc in presence of heat will give us benzene ring plus ZNO, right? Now coming to oxidation, phenol on presence of oxidizing agent, as we know, that is Na2Cr2O7 in presence of H2SO4 will give me benzoquinone. This is benzoquinone. Now finally coming to ethers. Alkoxy derivatives of alkanes are known as ethers with the general formula of ROR, right? Cn H2n plus 1 twice O. So these are again divided into simple or symmetrical ethers and mixed or unsymmetrical ethers. Simple or symmetrical ethers are when we have the same alkyl groups on both the sides, ROR, right? Mixed or unsymmetrical are when we have both alkyl groups are different, right? Now coming to the common name, we have dialkyl ether, right? For example, for this CH3O C2H5, we have what? Ethyl methyl ether as its name, right? And what is the IUPAC name for it? For usually ethers, it is alkoxy alkane. So for this example, it is methoxyethane. You should remember methoxy, lesser number of carbon atoms. So first methoxy, then ethane. Okay. Ethers exhibit chain isomerism and functional isomerism. Okay. Now coming to the preparation methods of ethers. So the first preparation method is from alcohols. So taking 2 moles of C2H5OH and reacting it firstly with concentrated H2SO4 at 140 degrees Celsius, we will get C2H5O, C2H5, that is what? Ethoxyethane, right? Plus H2O. And if I react the same 2 moles of ethanol with Al2O3 at 260 degrees Celsius, I will again get C2H5O, C2H5 plus H2O. Now what is the mechanism for it? We will get ROH, that is alcohol. On acidification, we will get ROH2. Again O is plus, right? So again reacting this with another ROH, that is alcohol, we will get ROR, right? Here we have R down, right? RO plus H, R plus H2O. And again removing that hydrogen, we will get R O R and H. On removing that hydrogen in presence of water, we will get ROR. Okay, ROR, that is what? Ether plus H plus. Now again example here for secondary alcohol is CH3 CHOH CH3 in the presence of concentrated H2SO4 at 140 degrees Celsius gives me CH, CH3, CH3O, CH, CH3, CH3, which is SN product. What is SN? Nucleophilic substitution ka product. Plus, it will also give me CH3, CH double bond CH2, which is what? Alkene, right? Which is E2 product or elimination ka product. Now, coming to tertiary alcohols. On reacting with concentrated H2SO4, they will directly give us only alkenes plus H2O. So secondary and tertiary alcohols undergo SN1 mechanism and give alkenes, whereas primary alcohols only give ethers, right? By the action of dry Ag2O on RX, that is alkyl halide. Okay, so we have alkyl halide plus Ag2O. Now this Ag2O can be written as AgOAg, right? So Rx plus AgOAg plus one more mole of Rx. I am writing this as XR. Why? Because I wanted to remove this AgX and AgX, right? So finally, I will get an ether ROR plus 2 moles of AgX. That is the silver salt of that halide. Now coming to Williamson synthesis, of course the named reactions are very very important. This is also important. Rx, that is alkyl halide plus NaOR, in, in the presence of SN2 reaction, it undergoes SN2 reaction and forms ROR, that is ether plus NaX. Now example for this, primary alcohol plus secondary. This is what? Primary CH3ONA, right? Plus this is secondary alkyl halide CH3CHCl CH3 will give me CH3CHOCH3CH3 plus one alkene, right? Now if I take tertiary, okay, tertiary alkyl group plus ONA and a primary alkyl halide, it will undergo SN2 reaction and it will give me 3 times of CH3COCH3 plus NaCl. Now coming to, if I take one more example, vice versa, that is tertiary alkyl halide I will take and primary alkyl group with ONA I will take. Then I will get an alkene plus NaCl plus CH3OH. So you need to observe the difference between these two equations as well, right? Now coming to aryl vinyl. Yeah, first we'll zoom it. Yeah, so aryl vinyl and bridgehead halides are inert to both SN1 and SN2 reactions at room temperatures. So we know what are aryl vinyl halides, right? Aryl are the halides which are directly connected to the benzene ring. Vinyl are when we directly connect the halide to carbon carbon double bond, right? One of the atom of carbon carbon double bond. So these all groups are inert to both SN1 and SN2 reactions at room temperatures. So now coming to physical properties of ethers. So C2H5O, C2H5 is colorless, highly volatile liquid and used as anesthetic. It is slightly soluble in water and readily soluble in organic solvents and are lighter than water. Its boiling point is lesser than alcohols due to the lack of hydrogen bonding. Now, what are the chemical properties? It is less reactive due to the non availability of active hydrogen bonding, right? Or active hydrogen, which enables hydrogen bonding. Now, they are not reactive with acids and alkali metals, etc. They do not oxidize and reduce easily. Ethers do not oxidize and reduce easily. The cleavage of bond. Firstly, the substitution in alkyl groups of ethers. Okay, so this is what it is, diethyl ether, right? So if I consider this group as alpha and this as alpha dash, okay, and reacting this diethyl ether with Cl2 in dark, okay, without sunlight, H mu is sunlight, right? So without sunlight in dark, I will get alpha alpha dash dichlorodiethyl ether, okay. And if I react it in the presence of sunlight, I will get perchlorodiethyl ether. So here you can observe the difference. In the first case, I am getting CH3, CHClO, CHCl, CH3. Second case, I am getting C2Cl5, O, C2Cl5 per chloro diethyl ether. Now, secondly, reaction due to ethereal oxygen. Okay, the oxygen present in ethers. So, firstly, what will happen? The formation of peroxide. Now, this C2H5OH, C2H5O and C2H5O, ether, diethyl ether. Okay, now this on oxidation will give me what? C2H5. This O will be attached to one more O, that is C2H5. Okay, and next is what? Formation of oxonium salts. If I have C2H5O, C2H5 plus HBr, now what will happen? This C2H5O will be having a coordinate bond with H. Okay, this arrow reacts a coordinate bond. So the coordinate bond with H and having a plus charge, and C2H5 Br minus. So this whole thing is called diethyl oxonium bromide, which is diethyl oxonium bromide. Okay. Now coming to the third one, that is the due to cleavage of CO bond. ROR plus HX, that is HX is what? Cold and as well as dilute. The acid halide should be cold as well as dilute, right? It will give me what? ROH, that is alcohol plus RX, that is haloalkane. Now if HI, it is reacted with HI, which is hot. Okay, so ROR plus HI in excess will give RI, that is alkyl iodide, 2 moles of alkyl iodide plus H2O. Now these are the various reactions occurring with C2H5O, C2H5. First, with concentrated H2SO4, it will give me ethanol plus C2H5HSO4, right? So if reacting with water, it will give me 2 moles of ethanol, right? Reacting with PCl5, it will give me 2 moles of chloroethane plus POCl3. If reaction with CH3COCl3 and AlCl3, it will give me CH3COO C2H5 plus C2H5Cl. So this is of course an ester, right? RCOOR, which is CH3COO C2H5 ester plus alkyl halide, that is ethyl chloride. Now if I react it with CH3CO twice O, then I will get 2 moles of CH3COO C2H5, which is again ester. If I react it with carbon monoxide or BF3 at 150 degrees Celsius and 500 atm pressure, I will get C2H5COO C2H5, which is of course a symmetrical ester, right? We have RCOOR. Next, if I react it with Al2O3 at 360 degrees Celsius, I will get 2 moles of ethene, right? Reacting diethyl ether with Al2O3 at 360 degrees Celsius, I will get 2 moles of ethene. Reacting K2Cr2O7, okay, reacting diethyl ether with K2Cr2O7, which means what? Oxidation, right? Ethers on oxidation, it will give me aldehyde, 2 moles of CH3CHO, again on oxidation, will give me 2 moles of carboxylic acid, that is CH3COOH. Now coming to electrophilic substitution reactions. First is halogenation. So this benzene ring attached to OCH3 plus Br2 in CH3COOH. It will give me bromine at ortho position and bromine at para position, wherein bromine at para position is the major product. Okay. Now, if I do nitration, that is reaction of this benzene ring attached to OCH3 with HNO3 and H2SO4, it will give me minor product of NO2 attached at ortho position. NO2 attached at para position would be the major product. And if I do Friedel-Crafts alkylation, that is reaction of that anisole or benzene ring attached to OCH3 plus CH3Cl, right, which is an alkyl group. CH3 is an alkyl group, right? Cl in the presence of anhydrous AlCl3. You should always remember Friedel-Crafts reaction, whether it be alkylation or acylation, they always need anhydrous AlCl3. Okay, so this on reaction with anhydrous AlCl3 will give me 2-methoxytoluene, which is this benzene ring with OCH3, and at ortho position it will give me CH3, or at para position it will give me CH3. So of course para position is of course a major product. So at ortho position the name is 2-methoxytoluene. At para position the name is 4-methoxytoluene, which is the major product. So with this we end our chapter known as alcohols, phenols and ethers. Okay, thank you for watching.